In the early 19th century, two brothers from Dayton, Ohio, tested their first glider designs on the windy sand dunes of the North Carolina coast. They were obsessed with the idea of flying, like birds, to soar over the infinite highway of the air, as Wilbur Wright called it, to conquer the fluid medium that surrounds us and that is so vital to all of the living creatures on the planet. The atmosphere is primarily composed of nitrogen and oxygen, but there is also, albeit in smaller percentages, a mixture of other gases in a delicate balance that is just right for organisms like us to survive. But what if that balance is altered? What if the air becomes polluted? Today, air quality is an international public health issue. According to the World Health Organization, air pollution is linked to 7 million premature deaths each year.
So there's a few areas of the country that are exceeding health standards that are set by the US EPA or even around the world with just global air quality standards.
There's about 100 to 200,000 premature deaths due to bad air quality in the US every year. That's, of course, a number that is way too high. It's higher than any of the natural disasters that you could have in this country.
We're trying to understand how we can best address that and improve the air that we breathe.
Understanding the interaction between the various chemical compounds that affect air quality will help us address a problem that affects people every day, especially in urban areas.
When events happen in cities, they typically happen on the order of hours or days. It's the emissions that we put in the air that day, and typically it can impact somebody's life that day. And so we're looking at how those pollutants evolve from when they go into the air to when it actually impacts the air we're breathing.
You know, when you burn coal or oil or natural gas, it's not just CO2 that comes out, but also these other gases, the NO2, the SO2.
Some of the gases that we actually emit, like nitrogen dioxide or NO2, actually only live in the atmosphere for about a couple hours before it's chemically transformed into something else. We call it a precursor because it's an ingredient for particulate matter, fine particulate matter that can be harmful for us to breathe in, as well as ozone, which is a harmful pollutant for us to breathe. It's very helpful up in the stratosphere. It blocks a lot of harmful rays from the sun, but we don't want it near the surface.
The ozone layer up in the stratosphere is very helpful to life on Earth because it blocks harmful ultraviolet radiation from the sun. But ozone is a toxic gas for living organisms to breathe. And ozone can form in the lower parts as a result of chemical interactions of the primary pollutants we emit.
And the only way to influence, for example, reducing our ozone as an air pollutant is to deal with those primary sources. So we really need to know which of those primary sources are contributing to ozone formation in the atmosphere so that we can kind of give that information and have a chance of improving urban air quality into the future.
So we really want to understand both the atmospheric chemistry and the climate impacts of pollution.
So we hope that this research that we're doing on this modern urban air quality that we're seeing right now will be used for regulators in the future to start turning this around, that we can still continue to improve air quality and really reduce these premature deaths in the future.
Cities and urban areas have grown tremendously since the Industrial Revolution, but this has led to serious air quality problems. We need to reduce pollution if we want to keep our populations healthy. The World Health Organization has recently published several studies and information on walking and cycling as a way to reduce urban pollution while contributing to exercise and a healthier lifestyle. Curiously enough, the industrial development of cities and the invention and use of the bicycle are closely linked in the history of modern times. Although the Wright brothers' passion was aeronautics, they had a bicycle shop in downtown Dayton that allowed them to fund their research and also manufactured the mechanical parts they needed to build their flying machine. In 1903, they achieved what is considered the first controlled flight in history, the first step in a revolutionary technology that continues to give us the means to explore and better understand our planet.
The Earth Science Division that we have at NASA is part of the Science Mission Directorate. And what we do is we look at the Earth, significantly utilizing the vantage point of space to study the whole planet, the natural components of the planet, human components of the planet, and the way humans and the planet interact over a variety of time scales and spatial scales, really trying to characterize Earth system behavior, understand the processes that drive it, be able to predict its future evolution, share all the knowledge that we get, and work to apply that knowledge to the benefit of really all the world's population in the US and overseas.
Better information about Earth processes will certainly help us understand how the system works. But how can we improve air quality? How can we know and monitor pollution levels?
So STAQS is this project that we started planning several years ago in anticipation of the launch of the TEMPO satellite.
TEMPO is an instrument on a platform in geostationary orbit. It is the first measurement that will measure air pollution from a satellite point of view every hour across greater North America, or at least trace gas pollution.
Ignition, engine full power, and liftoff. Intelsat 40E, go Intelsat, go Falcon.
Launched on April 7, 2023, the TEMPO satellite is expected to provide hourly air quality data over the continental United States for the next decade.
We're really excited about it. It launched just in April, and we're going to get some first measurements this summer. And so we're going to take out some enhanced measurements to make sure that TEMPO is operating like it should. We're getting great quality data so that people can actually use that to better understand their air quality challenges.
However, it is very challenging to measure surface ozone from a satellite because it would have to pass through the ozone layer in the stratosphere that protects us from the sun's harmful UV radiation.
So near-surface ozone is an air quality issue around the world, but it's really hard to measure the ozone pollution that is near the surface because we do have the stratospheric ozone layer above us, which is very important. We need that. So 90% of the ozone is above our head, and if you're at a satellite measuring downward, it's really hard to be sensitive to the surface. So one of the benefits of measuring ozone profiles from the ground up is that you're more sensitive to the air that's closest to your instrument. So we're not as impacted by the stratosphere. We can measure the pollution that's near the surface first and relevant to our air pollution before you get up to the stratosphere.
So what we really need is continuous measurements of ground-based profiles of ozone and other constituents. So what we really add to this campaign are profiles of tropospheric ozone, as well as column amounts of NO2, formaldehyde, other trace gas species that we're measuring from space. And what we're doing with these measurements is we're connecting them to the satellite measurements during all times.
Feeding ground-based ozone measurements and combining them with satellite data will help fine-tune models of tropospheric ozone pollution and distinguish it from stratospheric ozone.
So we have air at the ground, that we're measuring. We measure it in situ. So that's the air that we're breathing, and that's what's relevant to our air quality. But we can't have monitors everywhere. The other side of the spectrum is we have a satellite up at 22,000 miles away, and it can close the gaps between those monitors and understand how that pollution moves and evolves throughout the day. And then during STAQS, we also have airplanes that will go out for a small period of time and measure at higher spatial resolution.
During the STAQS campaign, 3 NASA aircraft will also take measurements and vertical profiles of ozone and other trace gases in the atmosphere, which will add to the overall data set and help improve the air quality products that the satellite will provide.
STAQS is, I should say, it's 3 airplanes. It's a combination of the NOAA Aroma Field Campaign and the NASA STAQS. So NASA and NOAA in partnership are going to fly the DC-8 to get vertical and horizontal distribution near the surface of the gases that Tempo measures, which is NO2, nitrogen dioxide, formaldehyde, SO2, as well as some information about ozone.
The story goes that Wilbur didn't want to fly over the city. He thought it was too risky, not only for himself, but also for the people below in case of an accident. Instead, he flew over the Hudson River, but still encountered strong wind gusts caused by the influence of the skyscrapers reaching for the New York sky, just like him. It was the first time such a large crowd had seen a flying machine. "114 years later, a very different kind of plane flies over the city. During this NASA campaign, 3 research aircraft will fly over various U.S. cities, including New York, Chicago, and Los Angeles, taking air quality measurements along the way.
So one of my favorite components about STAQS is actually how we're measuring. So we have the Tempo satellite that's up above our head, and we're stacking it with airplanes that are in the middle, giving us information about the vertical distribution of pollution, as well as measuring different gases that we're not measuring from a satellite, and connecting it to the surface where we're measuring surface air pollution and the air that we're actually breathing and is relevant to our air quality.
The DC-8, G3, and G5 take part in this airborne campaign.
So we have a variety of platforms that we can use in appropriate ways to address the science. And in many cases, we'll do campaigns with multiple platforms. Here in STAQS in the Aroma, we've got 3. We've got the DC-8, we've got 2 of what I'll call the business jets, the G3 and G5.
So we'll have the DC-8 flying in the lower part of the atmosphere, and then looking down from higher altitudes will be a Tempo airborne simulator. So I'll have similar spectrometer of Tempo, as well as we'll have a HSRL LiDAR that will give us the vertical distribution of the particles and give us some optical properties of the particles, which will also be helpful for Tempo, as well as ozone vertical profile. So we'll get some really valuable data to do science, understanding air quality in the 3 largest cities in the United States, as well as data to help us test out how well is Tempo really working.
Various instruments on board the aircraft will collect important data from several major cities, which will then be stacked with ground and satellite measurements to improve our understanding of air quality across the continental United States.
All right, so we transited from Dayton, Ohio to Baltimore. We have 3 stations here, and you can see the 2 instruments. The forward one is AVERS NG. It's a passive imaging spectrometer. And for this campaign, they're looking at the strong point sources, so they have swath of about 6 kilometers at this altitude. They're providing the image at different spectral bands, and from that they can deduce the strong point sources. The instrument ahead of that is the HALO instrument. It's a LiDAR, so it measures aerosol backscatter as well as methane columns, and we're trying to also measure some methane profiles as well.
While the G3 carries an instrument payload focused on measuring greenhouse gases, the G5 will collect data on trace gases, such as formaldehyde and nitrogen dioxide, both of which are ozone precursors.
So the G5 has 2 primary instruments on board. The first one is GCAS, the GeoCape Airborne Simulator. And this is the instrument that is closest to what Tempo is measuring. So it measures highly spectrally resolved ultraviolet and visible light. Its 2 primary products that we routinely retrieve are nitrogen dioxide, which is an indicator for fossil fuel burning. So we'll see peaks of that over the city. And we also do retrievals of formaldehyde, which is an indicator for hydrocarbon chemistry or active photochemistry.
In addition, the G5 can also measure aerosol particles and ozone.
So the second instrument that we have is HSRL-2, High Spectral Resolution LiDAR 2. It has the capability to profile aerosol characteristics below the aircraft, which is really interesting. Right now we are being impacted by some biomass burning in Canada. We can see some very interesting aerosol backscatter features near the surface, indicating urban pollution from Chicago. But also to tie in with the nitrogen dioxide and formaldehyde measurements from GCAS, HSRL is profiling ozone below us. So NO2 or nitrogen dioxide and formaldehyde are both ingredients needed to form ozone, which is what we're interested in this afternoon, as high ozone is forecasted to impact the communities on shore of Lake Michigan. And we also have the NASA DC-8 that is flying thousands of feet below us, profiling the atmosphere. That's contributing to the effort as well. So we're really excited to be here, and we're happy that Mother Nature, gave us what we were looking for on this day.
But making successful measurements of the atmosphere at different altitudes with different aircraft over major U.S. cities under heavy air traffic is no easy task. It takes skilled pilots to accomplish this feat. In 1910, the Wright brothers opened the first flying school in history, the Wright Flying School. Over the course of 6 years, they trained more than 100 pilots, several of whom became famous pioneers of flight, war aviation, and aircraft design. Today, pilots take us around the world. They protect us, rescue those in need, and even help us understand the world we live in.
817 is going to maintain flight level 180. You guys got to be the only DC-8 still flying. I think there's 2 of us. Yeah. You guys get to go to space? I'm only a research pilot.
Research pilots are experienced aviators who can take the airborne science platforms where the scientists believe they will get the most valuable data. Planning and coordination between the pilots and the science team begins long before the actual deployment begins.
We start out a couple months ahead of the science campaign itself, working with the researchers as far as where they want to gather data. We learn what air traffic control environment they want to gather data in, and we start coordinating with air traffic controllers. We get the waypoints that they want to go to from point A to point B on a particular line or a overfly of a point. We'll use that information to get permissions from air traffic control to do that type of work.
Flying a science campaign in heavy traffic carries the risk of interfering with commercial traffic. Each flight requires a detailed flight plan in advance to coordinate with air traffic control. But science objectives can change from one day to the next, depending on weather, atmospheric patterns, or pollution modeling. The ability to make changes in flight can be critical to the success of the mission.
So when we're flying a mission, if the scientist has a desire to change something, which happens almost every flight, we work with the specific air traffic controllers at that moment that we're in contact with, and then we ask them permission to change our profile. So that might be a change of direction, or it might be a change of altitude.
So changes in flight can be both very difficult and very easy. And when we're at high altitude, it gets more difficult the way that the U.S. airspace system is designed, where you always need to be with air traffic control, getting clearance for what direction you're going. But in a very congested airspace like LA Center that we've been working in, they've been very accommodating to letting us change direction, move around, and do somewhat unpredictable things. And they've done a great job at making sure that we're clear of other aircraft and not disrupting the normal traffic that is, a lot of people moving from different places.
In general, what we find needs change the most is the altitude we're at, because the high altitude clouds can affect the instruments that look down below the airplane, and also turbulence. If there's enough turbulence, you can get the airplane rocking a little bit about, and that affects the data. They do have means to correct for it, but the turbulence is something that we try and find a smooth platform for them as well.
For STAQS and Aroma, I'm on the G3, which you can see parked right there, NASA 520. And we've been looking for clear skies, and so today was a little marginal at the beginning with that marine layer over Los Angeles, but then we got improved throughout the day, and so we were able to fly over and have some beautiful views over Los Angeles. So that's some of what we've been doing with the STAQS Aroma.
Being a research pilot is not an easy job. It requires expertise and the understanding that each campaign presents new challenges.
Research piloting is it's a very fulfilling activity. As a pilot, having flown a variety of different airplanes throughout my career, it's fun to be able to fly multiple airplanes for NASA. And then it's really rewarding working with a team of scientists who have an objective to meet, and then we get to actually meet it as a flight objective.
I enjoy often the challenge of doing something different. So I'm not always excited when we have a change and the whole plan gets changed, but I think it's usually interesting to deal with.
By the end of the 19th century, major cities around the world such as London, Paris, and New York were drowning in horse manure. Along with the urine and corpses of the dead horses, it began to poison the city's inhabitants. The London Times predicted in 1894 that within 50 years, every street in London would be buried under 9 feet of manure. These concerns were quickly resolved with the development of the automobile industry, which introduced motorized vehicles on a massive scale. By the year 1912, the crisis had been resolved. But with it came a new problem. The development of modern cities has resulted in the generation of many pollutants, such as those from the burning of fossil fuels.
Air quality in urban areas have been changing. We're right now close to Los Angeles, and I think we all know that the air quality was really very bad in Los Angeles for decades now. But it's improving like every year since the 60s, basically. Air quality is getting better. Mostly because we're understanding what causes bad air quality, and especially because cars are getting cleaner and cleaner every year. So the last 10 years about air quality has not been on the same trajectory anymore as it's been in the past. So it's not getting that much better. And that's probably because of multiple reasons. One of them could be that the cars are by now getting so clean that they're not the major source of pollutants anymore.
Understanding air quality is complex. There are many chemical compounds that interact with each other to form new pollutants.
So primary sources are emitted from the ground. So these are things like nitrogen oxides and volatile organic compounds. And then secondary pollutants actually form in the atmosphere, so they're not directly emitted. And they're a little bit more complicated to kind of understand because you can't just measure what's coming out, they form in the atmosphere. But it's really important for us to kind of consider those primary sources because that's the only way to reduce those secondary sources of pollutants as well.
Tracking primary pollutants will give us an indication of the formation of secondary pollutants. But if primary pollutants have been reduced over the past decade, why hasn't the level of pollution dropped accordingly?
So to make pollutants like ozone, that's a secondary pollutant, you need nitrogen oxides and volatile organic compounds. Nitrogen oxides are emitted mostly by cars and trucks, and volatile organic compounds also by vehicles, lawnmowers, but also from volatile chemical products. We all use chemical products like cleaning products, personal care products, inks, prints, all these kind of things that we use in our daily lives are made to evaporate.
So these are VOCs that have been kind of under-researched in the past, and they come from personal care products, paints, all sorts of things that you use in your daily life that have a smell. Those often are volatile organic compounds, and your nose can kind of pick up on them.
So all of it gets into the atmosphere without much combustion, because the fuel that you put in your car gets combusted very efficiently in a new car specifically, and you don't add too many pollutants or volatile organic compounds to the mix in urban air.
VOCs, or volatile organic compounds, mix in the atmosphere with other primary pollutants to form secondary pollutants such as ozone, which is harmful to our lungs. After all, it takes two to tango, and if we want to improve air quality in the future, we need to track all possible sources of pollution.
So the atmosphere in the urban areas where we all live has been changing dramatically over the decades. But these volatile chemical products are basically stable and they're not going down as fast as cars.
And so we're investigating to try to understand what that mixture of VOCs looks like in the current environment and how much of that is contributing to kind of ozone formation and also aerosol formation.
Air pollution has been shown to be directly and indirectly responsible for many deaths around the world, and is one of the most pressing challenges we must address to protect people. The more information we have, the better we can respond. Wilbur and Orville were visionaries. They revolutionized the aviation industry, and they were not alone. Many others helped to develop new technologies, new breakthroughs in engineering, medicine, and science that contributed to the progress of society. All of these innovations were based on observation and experimentation. Making measurements and collecting good quality data are key components of any research process.
So one of the best ways that we can learn about air quality and air pollution in general is by looking at these types of measurements from multiple perspectives.
The integration of satellite measurements, airborne measurements, and surface measurements, as well as then collecting all the data, utilizing Earth system models to integrate it, produce hybrid model observation products, and also help us to think about Earth's future. But all of that's informed by the observations that we have.
Collecting data from the ground, aircraft, and satellites will help us build a more detailed picture of pollution and the transport mechanisms that affect it, so we can better address air quality issues.
We put all that together, this integrated observing system, and connecting those all together, we now have a vertical profile that can be used to validate the satellite and really understand the chemical transport or the air quality in the region like never before. And that is super important for the scientific community as well as our public health advocates.
You know, it's all an integrated piece in terms of utilizing these different vantage points to improve our knowledge about the Earth.
And just like the Wright brothers and others in their time, perhaps now is the moment to start a new revolution to meet the challenges of our century, to improve the lives of all of us who live on the same planet, Earth.